Okay, hello class. We will continue with our third part in this chapter. Okay, previously we have learned about the Maxwell relation. What is the importance of Maxwell relation? How can we measure or convert the unmeasurable parameter or thermodynamic properties to the measurable thermodynamic properties, such as from the entropy can be also converted or relate to the other measurable properties such as pressure, temperature, volume, and etc. So in this part, we will learn about the residual properties. What is the definition of residual properties and how to determine the residual properties? By the objective is you may estimate the entropy and enthalpy for the real fluid using the residual properties, and also to calculate the thermodynamic properties of the system at any specific condition. Okay, as the introduction, okay, from the Maxwell equation, we have learned about the correlation between the thermodynamic properties and the other correlation. Based on this example, we have the internal energy equal to TdS minus P dV, and we can also have another relation related or mainly used in this module. Okay, the canonical parameter is the function or the natural function of this thermodynamic property, such as for the first equation here, we have the internal energy, or if we turn to the based on its canonical parameter U equal to U, we have S and V. So we have this is known as the canonical parameter for the internal energy. Okay, for the second equation, we have enthalpy. Okay, enthalpy as function of S a P. So we have the Helmholtz here equal to Helmholtz as function of V and T, or volume and temperature. And as G is G as function of speed, T. So based on these canonical parameters, we can see that the most parameter can be easily measured if we have the Gibbs energy with only function of pressure and temperature. Okay, the pressure and temperature can be easily measured. The Gibbs energy, also known as the generating function, despite of other thermodynamic properties relation. Okay, the residual properties is defined as this actual of thermodynamic properties minus its ideal gas property. So the molar value of extensive thermodynamic properties, such as specific volume, we have the internal energy, enthalpy, entropy, and Gibbs. Okay, minus the actual. Okay, this it has the same temperature and also pressure. Okay, the residual Gibbs energy is defined as GR, or residual Gibbs, equal to the actual Gibbs minus the ideal gas Gibbs energy. Okay, if we arrange this, okay, example, if we refer to the volume, the residual volume equal to volume minus the ideal gas of the volume. If we know that the ideal gas here is equal to RT over P, so we can rearrange it and then we can determine the residual properties equal to RT over PZ minus 1. Okay, since the residual properties, also known as generating function for other residual properties, we may relate the Gibbs energy to other thermodynamic properties. Okay, example here, this is the relation of this Gibbs energy based on the enthalpy minus T S. So we arrange this equation and it's become the once we perform the Maxwell relation, the VR here equal to the GR, the function of GR over RT over dou P at constant temperature. We can get the value of how we can get the equation or the relation for the VR over RT. And then we also can get the another expression for enthalpy or residual enthalpy over RT by using this expression. Okay, through definition of Gibbs energy here, okay, we can get here when we perform the rearrangement. And then finally, once we perform the GR, HR, and also SR can be simplified to this equation by obtain the Z here. At constant, we have based on the constant temperature. So you may try your Maxwell relation to obtain this correlation. Okay, this equation is based on we start with it from 0 to arbitrary pressure. So it can be used or applied at constant temperature only. Okay, based on the equation from the Gibbs, we have the correlation or the canonical parameter based on the enthalpy and also the entropy, right? So for the example, for the enthalpy, the either when we arrange the HR or residual enthalpy equal to H minus HIG. So when we arrange the H here or enthalpy equal to ideal gas plus the residual. Same goes to the entropy. So we from the previous topic, we know that the dou HIG equal to CPIG dt, and then this is the equation to measure the ideal gas for entropy. And inserting this equation to obtain this, finally we can get the H here or enthalpy equal to enthalpy at ideal gas for the initial plus this. This is for this ideal gas HIG, and then this is for the residual. And same goes to the entropy. We have this equation for this ideal gas here, ideal gas, and also the residual. Okay, the residual properties have a validity for both gas and liquid, provide convenient base for the calculation of real gas properties. Okay, for the gas, residual enthalpy and entropy usually small as correction to the, or usually we can presume that the actual entropy will be equal to HIG for the gas system, because the SR is usually small or we can neglect it. Okay, for the liquid, the residual enthalpy and residual entropy are larger. We have the larger change, especially the entropy change of the vaporization. Okay, the calculating or determination of the enthalpy, usually we can use the heat capacity or specific heat and PVT data. Okay, but the PVT data from the experiment is difficult to obtain and usually is incomplete. So we may use the generalized correlation to determine the residual properties. Okay, the residual properties can be determined either by using PVT data or equation of state. Okay, back to our second chapter, we have learned about the equation of state, right? Okay, the equation of state can be classified either to be equation and generalized equation. Okay, the generalized equation is using the relation of the compressibility factor. Okay, if the pressure is lower, usually is below than 15 bar, we can use the virial equation. But if the pressure is higher, maybe above than 15 bar, you can use the Lee-Kessler equation by extract the data from the reference table. Okay, this is how we can determine the residual enthalpy and entropy from either by using the Lee-Kessler or generalized second virial equation or coefficient correlation. So for the Lee-Kessler, okay, this data you can obtain from the reference table, including the eccentric factor. Finally, you can determine the residual enthalpy. Okay, same goes to the entropy. SR0 and SR1 prime here, you can refer to your reference data. For each property or substance, it has own eccentric factor, and for each reduced temperature and pressure, it also has own SR0 and SR1. Same goes to the enthalpy. Okay, for the generalized second virial coefficient, okay, we may use this equation. And finally, we can get the dB0 and dB1 using this. Okay, the main thing that you need to define is the PR and also TR if we using the generalized second virial coefficient. So PR equal to P over PC and TR is T over TC. So for each substance, it has own critical pressure and temperature. Also, you may refer to the reference table. I think the value is given at table B1. Okay, let's take a break. Okay, in which condition of the pressure we can use for the virial and Lee-Kessler or generalized could be applied. What is the condition for the pressure to be used? If we have, we can choose whether the generalized or virial equation. So you may try answer it while taking your break. Okay, determination of delta enthalpy and entropy. So from this, we know that the enthalpy equal to, okay, if we after rearrangement, we can get the ideal gas plus the residual for enthalpy and also the entropy. Okay, from this we can consider the change of the state. Example, in the problem, the state 1 or the condition in state 1 is given and the state 2 also given. So you may use this, and then finally the state 2 and also state 1, we may calculate the difference of enthalpy. Okay, so this is how we rearrange it to determine the delta enthalpy by consider the state 1 and also the value of state 1 and also the state 2. Same goes to the entropy. You may consider it from this based on state 2 and state 1. Okay, the entropy and enthalpy changes can be summarized in the form of calculation path diagram. So we may proceed to the calculation path diagram by after we extract all the information in state 1 and state 2. Okay, I will show to you the example after this. Okay, how do we perform the calculation part to determine the delta H and delta S? Okay, example here. We have this real or the state 1, and this is the state 2. So in order for us to determine the real from state 1, state 2, we cannot it cannot be measured directly. So we cannot find the condition in state 1 and state 2 and then determine the delta H. But we need to move from the real to ideal state first. Okay, example here, the temperature and pressure is given, or we know that this is the real condition, and then we need to change it to the ideal state or ideal condition by determining the residual of enthalpy and entropy. And then after that, once we obtain the ideal gas or ideal state for the given temperature and pressure, we can move to the second state, but it consider ideal condition first. So to move from the state 1 to state 2, under the ideal state, we can determine the delta H at ideal state as well as delta entropy at ideal state. And then after we obtain the ideal state for the second state here, or ideal condition for the second state, we can move to the real in state 2 by determining the residual or the residual enthalpy and entropy. Okay, the difference between the first part here and the third part here. Okay, maybe just okay, this is our first part, our second part, and this is our third part. So to determine delta H here, we need to sum. Okay, perform the summation for all part here. Okay, the difference between the third and also the second part here, you can see that for the first part, from the real to the ideal, so we have the negative sign here. But from the ideal to the real, we have the positive sign, or known as the second state. Okay, this is how we perform the or determine the delta enthalpy and delta entropy. Okay, in overall, delta H equal to, okay, we can determine the ideal gas here. So by using the CP, okay, we may have the different temperature in state 1 and 2 state 2. Okay, we can have the determine the CP here, and then plus HR, okay, at the second state and the first state. Okay, this value you can obtain from your reference table. Okay, same goes to the entropy. We may consider the CP first. Okay, from the state 1 to state 2, and then we may determine the SR here from your reference table. Okay, the next condition, if mentioned about the ideal condition at the initial or final state. So any condition, if any problem, if it mentioned about the ideal condition, so we may have the trapezium calculation part. Okay, like shown in this figure. So example here, if the question is given, the second state is performed at ideal state or considered at ideal state. Okay, example here, the initial condition is in ideal state. So in order for us to determine the delta H or delta S, you may start with, okay, this is our first part from the ideal. No need to convert the real to ideal state anymore, because our initial state is in ideal state. So from the ideal to the ideal, so we can get the delta Hij and also delta Sij. Okay, from the ideal second state, we can straight away move to the real second state here. So we have the second path here, SR, and we have this HR. This is our maybe SR2. Okay. So same goes to the, if we have the ideal at final state. Okay, this is at your initial, or if we have the ideal at final state, you may use the this or perform this trapezium diagram. So we start with the ideal with the real to the ideal. So from the real, we need to convert it to the ideal. So it turns to, this is our first part and this is our second part. Okay, so for the first part, we have this minus H of 1, and for the entropy minus S1 R. So this is our delta Sij and delta Hij, because we have the ideal and ideal. Okay, the condition is it should be either one where the initial or final state should be in ideal gas. And then after that, if we have this involved, there is a reaction of phase change. So you may consider where the heat reaction or latent heat must be considered to perform your calculation part. Example here. Okay, the first state here, okay, mention about this certain temperature and condition. And then maybe the first state is the substance is in vapor state. So we may have this. Okay, we may consider it from the real to the ideal first. And then from the liquid, okay, maybe this is the vapor phase. And then we need to move to the liquid phase first. So by consider the different phases here, we have vapor to liquid. So we need to consider where the heat of reaction of latent heat. So it depends on the given problem given. So and then after that, we can move from the liquid. We have the same phase here, from the liquid in ideal gas to the liquid in the second state, also in ideal condition. And then finally, we can get the real of this at the given temperature and pressure. So this is how we perform the calculation part if involve the reaction of phase change. Okay, and then if the given state or initial state in ideal condition, so you may consider it to convert from the ideal to ideal, but you may consider it based on the changes from the maybe from the vapor here to the liquid. So anything you need to ensure that the phase or the reaction it has the same phase to convert from the ideal to ideal, or delta Hij and delta Sij should be or should have the same phase. Okay, from the example here, the butane, okay, the first butane vapor at 200 degrees Celsius and 70 bar is set equal to 0 for saturated liquid at 0 degrees Celsius at the initial state. Assume the only data. Okay, the question is design the calculation part. Okay, so the set equal to 0 for saturated. Okay, so our first state is, okay, we have a liquid and 0 degrees Celsius saturated. That means we have at 1 bar or 1 atm actually, or 1 atm. So 1 atm or equal to 1.771 bar. And then we have, okay, second state is vapor. So maybe I write up the name of the substance as well. Okay, 1 butane. So we have one butane, a vapor. Okay, the first state in liquid, and then we have 0 degree and saturated. So saturated we can consider at 1 atm, so equal to 177 bar. Since the unit in bar, so standardize the unit. So we have the second is 1 butane. So we have the vapor, and we have 200 to 70 bar. Okay, design the calculation path. Okay, we should start with 0. Okay, our first in liquid. So we have this is this from the the first state is 0 is 2.15 K, and then we have 1.77 bar. So our second state is at 471 K and 70 bar. So we need to perform the calculation path here. So our first in, okay, maybe I should write this in the liquid, and this is the vapor. Okay, the first path is, okay, this is the real, and this also a real. So we need to convert to the ideal, right? To convert it to the ideal, so we need to have the same, okay, the real to real first. That means because we have the liquid to vapor, we need to convert it to the vapor first. So we have this one. Okay, this is our first part. Okay, so our first part, it convert from this 273.15 K to 1.77 bar and in vapor. So our state in vapor, and then after that our next move is to convert it from this vapor to the ideal vapor. So we have 273, we have 273.15 K to this vapor, or this is turned to be real, 1.77 bar to the ideal. So we have our second path here. And then from the ideal to ideal, we can perform the ideal. So it turns to 473.15 K at 70 bar in ideal. And then from the ideal, we can move to the real. So this is our third part, and this is our fourth part. So we start with from the real to real, but we need to change the phases first. So we need first to change the phases. From the liquid to vapor. So we can determine the latent heat here, delta H LV. So this is our delta S LV. And then from the real to ideal, we can have the minus H R or residual. Maybe this is our first part, and then one at the or real for entropy. So from the ideal to ideal, we can determine the delta Sij and delta Hij. Okay, the last part is ideal to real. So we can determine the SR or the second, HR second. So, and then the total here, okay, for the first page, and then we proceed to the real, change from the real to ideal. So it gives us the residual, right? And then the third is change the state at ideal, and then the last is change to ideal, from ideal to real. So this is the step, and then the total here, or total delta H here, you can obtain the delta H if the question asking you to determine the delta H is delta H LV plus H1R plus delta HIG plus H2R. So this is you can obtain from the your reference table. So for the import the IG or ideal gas, you can use this CP for both entropy and enthalpy. Okay, heat or the enthalpy change also can be based on the heat of reaction and heat of formation. Okay, the chemical reaction always followed by heat transfer. Enthalpy change during a reaction called as heat of reaction. Okay, the standard heat of reaction can be determined from standard heat of formation. We can determine that R here, or standard heat of reaction, from the heat of formation based on the compound from, or the element from given in the table C4 in your appendix. Okay, the formation of a reaction is based on come from its element. That's mean if we have maybe ammonia, so it comes from this N2 plus H2. So this element, it has own heat of formation. So you may refer to the your reference table. Okay, a common chemical reaction can be written as follow by consider the stoichiometry coefficient. Okay, the stoichiometry coefficient with general signs convection. Okay, for the positive, we have this stoichiometry at product. So if this is our product, okay, so it gives this positive stoichiometry coefficient, and for the reactant, it gives this negative value. So this is our product and our reactant. Okay, the standard heat of reaction usually at 25 degrees Celsius can be determined using this heat of formation, and then we may also calculate it based on the based on the product and reactant. Finally, we can get the heat of reaction at given temperature or other temperature using this expression. Okay, the residual thermodynamic properties can be applied in a mixture of gas. Okay, but we need to determine or use this correlation or related to the pseudo-critical parameters such as eccentric factor or the critical temperature and critical pressure. So all this information you may refer from your reference table. Okay, and then this is how we determine the reduce temperature and pressure. Okay, the critical is from the reference table. Okay. Since we already learned how to determine the residual from our previous chapter, right, in volumetric properties. So I hope that you still can recall, or you can recall the calculate how to calculate this reduced temperature. Okay, if involved the gas mixture, example, we have A, B, C as the substance for the gas, and you may tabulate it in the table. So this is the composition for each for each substance. Okay, the eccentric factor for each reaction or for the mixture can be determined based on the summation of the for each composition times the for each individual eccentric factor for the gas here, and same goes to the critical temperature and pressure. So you need to know what is the composition for each species. Okay, let's take a look on the example here of propane gas at 1 bar and 35 degrees Celsius is compressed to a final state. So our first state here, is we have propane. So we have gas in 1 bar and 35 degrees Celsius is compressed to a final state. So we have propane. So since it compressed, so we have a gas as well. So 135 bar and 195 degrees Celsius. Estimate the molar volume. So we need to determine the molar volume of the propane in the final state. Okay, and enthalpy. Okay, so we need to determine molar at final state and change of enthalpy and entropy. So the answer is given. So we need to determine this molar volume and delta S. So we need to start with the perform the calculation part. So the ideal, okay, the first state here, okay, given here is 1 bar 35. So it consider the ideal. Okay, any ideal, since this is gas, you may refer to the value of pressure. So any condition or any species at 1 bar, so it considered as ideal condition. So we have ideal here. From ideal to the real. So we have real here. We have this is 35 degrees Celsius and 1 bar. And this is at 150 degrees Celsius and 135 bar. So we need to move from this first state to the second state. So the ideal, since this is ideal, so we can determine the delta Hig and delta entropy at ideal gas. So we already have the ideal to ideal from initial to the final state. And then from the ideal, we need to move to the real. So we need to define your residual entropy and enthalpy. Okay, so we need to extract the information from table B. You need to determine the propane. What is the properties for the propane? So this all the information written in table B1, and then the estimate molar volume in final. So we need to start or determine the molar volume in final. So we can find the using the V equal to ZRT over P. So RT, we can obtain the RT, T also given, P also given. So you need to determine the Z. Okay, for the final state, this is the higher pressure. So you may use the very generalized equation. So this is the correlation here. You can use this correlation. Z naught and Zy can be obtained from the Lee-Kessler or using from the table E, or known as the Lee-Kessler table, reference table. So this is the information that you need to extract, or you need to calculate this PR first and also the TR in order to determine the Z. So the range of PR here is 3.178 and TR is 1.3. So you may use your calculation to perform your interpolation. And then we can get the value of TR and a value of Z node, and also same goes to the Z1, and insert this value Z node and Z1, you can get the value of Z by consider the eccentric factor as well. Finally, we can get the value of a molar volume here after we define our Z. Okay, the next is to determine the delta H. Okay, delta H based on the calculational part here. Okay, delta H is summation of the delta ideal gas and also the residual at second state. So for the ideal gas, you can use this equation since Cp is for the propane, you may refer to table C1. So insert this value and then perform the integration from T1 to T2 of the Cp. Okay, so we have here example here. You may for the integration, so you need to add a T here. So we need to add T and then it turns to T2 and then this is our T3 over 3. So this is over 2. So this is how you solve and then perform. Okay, you may also use your scientific calculator to solve this, perform this problem. So finally, you can get the answer. Okay, the delta Hij is equal to this value. And then next, to perform or determine the residual of the enthalpy. So this is the equation to solve the residual enthalpy. So we need to define the HR over RTC. So this value also can be obtained from your table. So you need to perform the interpolation here. So you may refer to this table E as well. And then after that, you can obtain the residual of enthalpy by times the universal gas R here and also the TC. So and then finally, the total up the delta Hij, the value of delta Hij or enthalpy at ideal gas and also the residual for your second state, we can obtain the delta H. Okay, for the entropy, we use the same method. We need to determine the delta S at ideal gas first. Okay, this is the equation. Okay, you may use this equation and then perform the integration here. And then you can use also your scientific calculator. Finally, you can obtain the delta Sij. Okay, next, okay, we already determined this. So you need to determine the residual of entropy. Okay, you may use you may refer to the table E as well to obtain the SR. Okay, so same, use the same procedure as we determine the enthalpy or residual enthalpy. And then finally, you can obtain your SRs here. And then the total or the delta S here is by total up the delta Sij and delta, or not delta, but SR for the second state. Okay. Okay, for the next problem, estimate the value of V molar volume, the residual enthalpy and entropy for equimolar. Okay, if we have the mixture. Okay, the first is carbon dioxide and second compound is propane. Okay, the given the temperature and pressure is given. So from this for any mixture, okay, for the mixture, Okay, you need to determine the entropy, and then example the critical temperature, the critical pressure. So you need to base on your or the submission of Y or 2. So we need to determine the composition. So we have TCI, YI, and also your PCI, YI. Okay, and then from the table E3 and E4, we can determine the reduced temperature and pressure. So by using this, since we have only two gas here, or we have the composition is also given equimolar. So we have 0.5 and 0.5. So finally, you can obtain your eccentric, critical temperature and critical pressure. Okay, to determine the molar volume here, so we have to using the Z RT over P. Okay, and then the temperature and the pressure here. And then, okay, this is how to solve this or define the HR or residual enthalpy here. You may use this equation. Okay, and then you may refer to the table to determine this HR0 and HR1. And then finally, you can obtain the HR. Okay, same goes to the entropy. So you may try this. I already provide the answer. And then you may try this and refer to your reference table. Okay, because this is the straight away calculation. Okay, in summary, we already defined what is the residual property. So residual properties is equal to the actual minus the properties at ideal gas. Okay, usually the residual properties is can be used for ideal for the gas state. Okay, the residual properties can be determined either by using the generalized equation using the virial or Lee-Kessler. Okay, Lee-Kessler can be applicable at higher pressure usually or above than 50 bar. The higher than 15 bar. Okay, if we have higher than 15 bar, so you can use this the method by using Lee-Kessler, refer to your table. And then for the virial equation, if the given pressure is lower than 50 bar, so you may apply the virial equation. Okay, to test your understanding, okay, please illustrate the calculation path diagram for each scenario given here. So you may state from the state 1 to state 2, okay, based on the scenario given here. Okay, and then okay, since we already covered the topic of the residual property, so I hope that you can try the example by your own and you may try to check the with the answer given in the example. So I'll see you for the next part or our last part in this talk in this chapter. Okay, bye.